Law by Faraday. So introduction. So the purpose of this lab was to witness the interactions between the magnetic fields of the magnet and the surrounding metal pipe, and to witness how magnetic fields, forces, and currents are created and influence each other, and to compare the experiment to the created computational model. So our results preview: the experimental time was 1.112 seconds, and the computational time was 1.486 seconds. So the principles that we used were Ohm's law, which is I equals V over R, the Biot-Savart law, which told us the magnetic field of the magnet. So this is the dipole magnetic field, the magnetic flux equation, and Faraday's law, and Newton's second and third law, which was F equals ma. This is Faraday's law, and this is the magnetic flux, or no, yeah, this is the magnetic flux. So our initial conditions were that the length that I measured were the length of the foil was 0.46 meters, foil thickness was 0.6 centimeters, the inner radius, outer radius, the mass of the magnet was 0.025 kilograms. The systems were the magnet in the foil tube, and the surroundings were everything else. So we made a couple assumptions. We assumed that air resistance was negligible. The magnetic force and the gravitational force are the only forces acting on the system, and the bar magnet is a perfect magnetic dipole. And I expected that the computational model and the physical experiment values would be similar. So in our experimental model, we were supposed to drop a magnet down the aluminum foil and measure the time it takes for the magnet to fall through. We were supposed to repeat that experiment 5 times and take the average for our measured time. So this is the foil and this is the magnet. This is my code. So these are the outputs. This is my velocity versus time graph. And it says it took it 1.486 seconds. And this is like the magnet falling through the tube. So this was the code using the Biot-Savart law. I found the magnetic field of the magnet through this. And then we calculated the change in flux, which we then used to find force. And then we found the force of the ring. And then we also found the force of gravity, and then we used that to find the velocity and all that other stuff. Which color corresponds to clockwise current as viewed from above, and which is counterclockwise? How do you know? So the red is counterclockwise and the blue is clockwise. We know this by using Lenz's law, which says that the magnetic field from induced currents oppose the change in flux. What happens to the dynamic of the system when you flip the magnet around? If we were to flip the magnet around, the direction of the current would flip, but the magnet will follow the same motion whether or not the north side is facing down. How does the total time in tube of your real-world system compare to that of your computational system? How might the computational system be more accurate? The real-world system is similar to the computational system, but is 25% less. So that was my results. The computational system is more accurate because it gets rid of human error, air resistance, and external forces. What does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? So before the magnet enters the tube and after the magnet exits the tube, the gravitational force is greater than the magnetic force, which you can see because the velocity of the magnet becomes more negative. When the magnet is inside the tube, the net force is 0. The magnetic force is equal to the gravitational force, so the acceleration is 0, and the velocity of the magnet is constant. Here are my results. So the experimental time I got was 1.112 seconds. The computational time was 1.48 seconds, and the percent difference is 25.17%. So what if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? Due to the equation I equals V over R, reduced resistance will increase the current. This would cause the magnet to fall even slower because it will take less time for the magnetic force to equal the gravitational force. What if holes or slots were cut into the tube? How would this affect the ring current in your model? There would be less complete rings, therefore decreasing the magnetic force by the magnet. This would cause the magnet to fall faster. And my possible sources of error are mistakes in my timing and air resistance acting on the system. Conclusion, in this lab, we learned about Faraday's law and modeled its effects through a physical experiment and computational model. We also learned about all the other laws and theorems that created it, such as the flux equation, Ohm's law, and many other principles. Thank you.